Hello everyone, this is Erlin from the Experience Research Lab. Today I'll show you how to run a binary logistic regression in Microsoft Excel. As mentioned in the previous video on how to run linear regression in Microsoft Excel cannot read SPSS files, not to mention import them directly to the platform. However, by downloading and installing the professional package of Colectica that costs only $1 per month, I can easily download such files not only from SPSS but also from Stata and SAS. To analyze the data, I can use the Microsoft Excel data analysis tools that allow me to run several types of analysis, including ANOVA, correlation, covariance, and regression. Further, if I want to run a more advanced statistical analysis, I can download and install the Real Statistics resource pack that is literally free of charge. And actually, this is what I will use for the analysis in this video today. But before I run the analysis, I will first import the SPSS files from SPSS by clicking from SPSS. When the dialog box pops up, I will click this button with three dots here and locate the folder where the file of dataset I want to analyze belongs. So the file name is bank loan. It's selected here and then click open. To import the files, I simply click import. So as shown on the right pane here, the dataset has 12 columns. And if I press Ctrl N, I can see there are 851 rows. Since regression analysis in Microsoft Excel cannot work with rows with empty cell, I need to first check the column one by one. So the first column is for the age in years. If I go to home and sort the value from smallest to largest, I can see there is no row with empty cell here. Column B is for level of education. It has several values coded as 1 for did not complete high school, 2 for high school degree, 3 for some college, 4 for college degree, and 5 for post-undergraduate degree. Column C is for years with current employer. Column D is for years at current address. Column E is for household income in $1,000. Column F is for debt to income ratio. Column G is for credit card debt in $1,000. Column H is for other debt in $1,000 as well. And column I is for default history. This column has two values coded as 0 for no and 1 for yes. So if I sort this column I from smallest to largest again, I can see there are so many rows with empty cells here. And if I scroll up, I can see actually there are only 701 rows completed, while the other rows left empty. So what should I do with the rows with empty cell here? As also mentioned in the previous video, I actually have two options. The first option is to remove the rows with empty cell, while the second one is to replace the missing values in every empty cell with the mean or average value of the column. In theory, removing the rows with empty cells is far more reliable, especially when I have large sample size. So for the analysis in this video, I will go with the first option. But instead of removing the rows with empty cells from the dataset, I will just exclude them from the binary logistic regression. By the way, logistic regression is pretty similar to discriminant analysis because both use independent scale variables to predict the categorical dependent variable. There are several types of logistic regression. Among others are binary, multinomial, ordinal, and Poisson logistic regression. The logistic regression I will run today is binary because the dependent variable default only has two values coded as 0 for no and 1 for yes. So the objective of the binary logistic regression that I will run today is to predict the likelihood for people to default on their bank loans based on their age, level of education, years of working with the current employer, years of residing at the current address, household income, debt to income ratio, credit card debts, and other debts. To achieve the objective, I will type add-ins here. And then browse for the real statistics pack that I have downloaded in download folder. And then click OK. Now I'll select this X real statistics and click OK. Now I can start to run the analysis by clicking add-ins, real statistics, and data analysis tools. On this dialog box, I will go to the second tab rack and find the logistic and probit regression. Click OK. So the input range here is for all variables that will be used in the model. So it will be column A to column I. Click fill, but because I only have 701 rows filled in, I'll change this to 701. And since the first row of the dataset is for headings, I'll tick this box, column headings included with data. I also want to see the item by item details in output. And hide the ROC table. ROC stands for Receiving Operating Characteristics. It hints at the best cutoff value for predicting whether someone will default or not. It is not a must-have because it also comes with a plot. So I will leave this box unticked. So there are two types of regression here. The first one is logistic and the second one is probit. Both are logistic regressions and essentially have the same interpretation. The difference is that the logistic model uses something called the cumulative distribution function of the logistic distributions, and the basis is an assumption of extreme value type errors. Meanwhile, the logistic model uses so-called the cumulative distribution function of the standard normal distribution. The basis is an assumption of normal error. The data in this dataset is raw data and I want to analyze it with Newton's method. I want to be confident that there is only 5% chance of being wrong. That's why I have the alpha of 0.05. Meanwhile, the classification cutoff is 0.5. It means that if the score is less than or equals 0.5, the observation will be classified as non-defaulters. But if the score is higher than 0.5, it will be classified as defaulters. A binary logistic regression takes an iterative procedure to achieve the maximum likelihood. The number of iterations here refers to the maximum number of times allowed to update the parameters until they converge. For the output, I want to have it printed in the first row of column N. So I'll just type N1 here and then click OK. So this is how the output of binary logistic regression in Microsoft Excel looks. The first table is probit regression, but I'll come back to this table later because I want to start the reading from the table below. Looking at the coefficients in this table, I can say that the likelihood to default on bank loans have positive relationship with age, level of education, debt to income ratio, credit card debt, and other debts. So the higher the credit card debt, the more likely is someone to default on his bank loan. On the other hand, the likelihood has negative relationship with years of working with the current employer, years of residing at the current address, and household income. So the longer is someone working with the current employer, the less likely he is to default on bank loan. SE in the third column stands for standard error. It provides the absolute measure of the typical distance between data points and the regression line. The lower the value, the better it is. Volt in the fourth column determines the significance of an independent variable used in the model. The higher the value, the better it is. P-value in the next column tells pretty much the same information. A small p-value of lower than 0.05 like this indicates a significant relationship between the dependent and independent variables. So out of these 8 variables used in the model, only 4 have significant relationship with the likelihood to default on bank loans. The 4 variables are years of working with the current employer, years of residing at the current address, debt to income ratio, and credit card debt. LL stands for log likelihood. It measures the goodness of fit for a model. The value may range from negative infinity to positive infinity. The higher the value, the better the model fits a dataset. Nevertheless, it cannot stand alone and serve as the only index of fit. That is to say, I need to have a look at the chi-square, which indicates the model ability to predict the values with or without the predictors. The higher the chi-square, the better the ability of the model to predict the values. The F stands for degree of freedom. It is the number of variables used in the model minus 1. So it is basically the number of independent variables, which is 8. The p-value indicates the significance of the relationship described by the model. The lower the p-value, the more significant the relationship is. As you see here, the p-value is very, very low. It means that the relationship described by the model is significant. As configured in the setting, alpha is 0.05. R squared shows the proportion of the variance for a dependent variable explained by the independent variables in the model. In scientific research, R squared is supposed to be higher than 0.6. However, in marketing and social research, it can be as low as 0.1. So R squared of 0.31, 0.30, and 0.44 here are not necessarily a bad sign. AIC stands for Archaic Information Criterion. It adjusted to restricted log likelihood by twice the number of parameters in the model, while the BIC stands for Bayesian Information Criterion. It adjusted to restricted log likelihood by the number of parameters times the log of the number of cases. Small values of both AIC and BIC indicate better models. The covariance matrix here indicates the relationships among variables used in the models. The value may be either positive like this or negative like this. A positive value indicates the same direction. If one variable increases, the other one also increases, while the negative value indicates the opposite direction. If one variable decreases, the other one increases. It is an inverse relationship. Before I continue, let me quickly copy the headings from the dataset. and paste them to the rows here. And columns here. Looking at this covariance matrix, I can say that the likelihood to default on bank loan has a positive relationship with age. I just highlight it with yellow, and other debts here. It means that when age increases or someone gets older, the likelihood to default on bank loan also increases. Likewise, when the amount of other debts increases, the likelihood to default on the bank loan also increases. Now let's have a look at the relationship between other debts and other variables. Here I can see that other debts has positive relationship with age and level of education. It means that when someone gets older, the amount of other debts also increases. For some reason, someone with higher level of education has higher amounts of other debts. Let's take another example to see the negative relationship between variables. Here, credit card debt has negative relationship with age, level of education, household income, and other debts. Obviously, it also has a negative relationship with the likelihood to default on bank loan. It means that when someone gets older, the amount of credit card debt decreases. And people with higher level of education has lower amount of credit card debt. This is really interesting. Now let's move to the next table here, the converge table, which shows where the parameter estimates converge given the maximum number of iterations for the binary logistic regression. If I block this table, click insert and click recommended charts, I can select these charts and click OK. I just move it down a little bit. I can see that the parameter estimates actually converge in the third iteration and gets back to the closest position in the nth iteration. The next table is the classification table. It has 4 columns and 3 rows, where the second column presents the number of observations classified as defaulters. So I just type defaulters here. With a cutoff value of 0.5, there are 183 defaulters. However, the model correctly predicts only less than half of this group. The third column presents the number of observations classified as non-defaulters. With the same cutoff value of 0.5, there are 517 non-defaulters. Here, the model correctly predicts more than 90% of the observations. So overall, the model correctly predicts 81% of the observations. I will not talk much about the ROC table because the output comes with a ROC plot, but I'll just quickly go to the last row, where I can see the total AUC equals 0.85898. If I just quickly grab the plot, and drag it here next to the table. I can show you what this 0.85 means. With an AUC of 0.86, I can say that this model does an excellent job in predicting the likelihood to default or not default on bank loan. If I just click draw and grab a highlighter, I can show you where this 0.86 is located. So it is here under the curve. So if it is a whole portion, 100%, an AUC of 0.86 means that the model covers 86% of the observations on the data set. Now let's go back to the first table, our probit regression table. The first 9 columns here is exactly the same as the first 9 columns in the data set. So there is age, level of education, years of working with the current employer, years of residing at the current address, household income, debt to income ratio, credit card debt, other debt, and success. So this is where the difference starts, where default in the data set is now success in the probit regression table. The next column, failure, is technically the opposite of success. So if it is 0 in column V, it must be 1 in column W. And if I just scroll down, I can show you that if it is 1 in column V, it must be 0 in column W. Therefore, the total in column X must always be 1. Column AA presents the scores that will be used to predict the likelihood to default on bank loans, and column AB is technically the other side of the column AA. So if it is 0.33 here in column AA, it must be 0.67 in column AB, because the total of these two columns must always be 1. So this is 1 here. It's also 1, 1, 1, and 1. Column Z is basically the copy of column AA. And since the scores is lower than the cutoff value of 0.5, the model prediction classifies it as non-defaulters. So non-defaulters here in the prediction and non-defaulters in the observations. That's why it is 100% correct in AD. Now if I scroll down to the last row of this table, I can see that the model correctly predicts 81% of the observations. The question is that, is it possible to improve the accuracy of the model prediction? And to answer the questions, I'll quickly go back to the classification table and briefly talks about the type 1 and type 2 errors. Incorrectly classifying the defaulters as non-defaulters leads to false positive results. This is also known as type 1 error, and a high number of these may jeopardize the business because there will be so many people are not coming back to pay back their loans. Meanwhile, incorrectly classifying the non-defaulters as defaulters leads to false negative errors, which is also known as type 2 errors. A high number of these type of errors may halt the business and customers' growth. So the answer to the question will actually depend on the business objectives. If the objective is to minimize the risk, I can try to improve the accuracy of the model prediction by decreasing the cutoff value to 0.45, for example. Consequently, the type 1 errors will decrease to 79. It means that the number of defaulters wrongly predicted as non-defaulters will decrease to 79. So that is how you run and interpret the output of binary logistic regression in Microsoft Excel. If you have any questions, please feel free to leave a comment. For more insights into data, including data entry, data transformation, and data analysis in SPSS and Microsoft Excel, please feel free to subscribe, listen, and watch our content. It is available in text, audio, and video format. Thank you for being with me today. I'll see you next time in the other videos. Cheers!